Hello everyone, in the last video we talked about variable separable types of differential equations. In this video we're going to be looking at homogeneous first order differential equation. In a nutshell, a differential equation of the form, say p of xy dx plus q of xy dy is equal to 0 is said to be homogeneous in x and y if both p and q are functions of x and y and they have the same degree throughout. Example, if I have a function, say f of xy is equal to x squared plus 2xy plus y squared is equal to 0. This function is homogeneous in x and y because the degree of x in the first term is 2, the combined degree of xy is 2, and here is also 2. That means that the degree is the same all through. Therefore, it is homogeneous. However, if I have a function, say g of xy is equal to x squared minus y all over 2x squared plus y squared. This equation is not homogeneous because here we have the first term has a degree 2, the second term has degree 1, and other ones have degree 2. Therefore, because of this imbalance in these degrees, in these 2 degrees, and this one, we say that it is not homogeneous in x and y because of this y term. We're going to be looking at a few examples, but before we do that, I want to list out procedures of solving homogeneous first order differential equations. It is very good to understand that homogeneous equations, most homogeneous equations in x and y are not variable separable directly. So we have to make certain assumptions in order to solve them using separation of variables. Therefore, to solve homogeneous differential equation, the first thing we do is to rearrange if we want to. We rearrange the equation. Number 2, we assume that y is equal to vx. And number 3, we find dy dx from vx, from y equal to vx. That is from here. And finally, we do what? We separate our variables. We separate variables and our solution, when we would find our solution. So we're going to take an example to see how this actually works. Consider the differential equation. I'm going to use a fresh page. Consider the differential equation 2x plus y dx plus x dy is equal to 0. This equation, of course, is not variable separable. If you want to know why, you should look at my previous videos. Since it is not variable separable, it is, however, homogeneous in x and y. If you look at it, we find out that all the powers of the variables are even all through. Therefore, we make the first assumption. We can rearrange if we want. We can leave it if we don't. Then we can assume that y is equal to vx. So the first thing is to let y equal to vx. Therefore, we can use product rule to find dy dx. So therefore, we can use product rule. We say dy is equal to v dx plus x dv. So we can now substitute this 2 into 1. So that we have 2x plus vx dx plus x into v dx plus x dv. So when we bring out x from this place, from here, we have 2 plus v x dx plus x into v dx plus x dv. So if we divide through by x, we'll be having 2 plus v dx plus v dx plus x dv. Here, we have succeeded in simplifying it further. So we can choose all the terms that have the x to one side and the terms and the other terms to the other side, so that we can have 2 plus v into dx plus x dv is equal to 0. Sorry, all these are equal to 0. Now, you would notice that the equation has been reduced to a variable separable equation in x and v. It used to be an equation in It used to be an equation in y and x, and now it is an equation in x and v, which is separable if we look at it. So we can simply write here that this is 2 plus 2v dx plus x dv is equal to 0. So to separate these variables, I can simply have 2 plus 2v dx is equal to negative x dv, so that I can have that dx, negative dx all over x, is equal to dv all over 2 plus 2v. The variables has been separated. So what we have to do is to integrate both sides. So we have negative integral of dx over x is equal to integral of dv over 2 plus 2v. So I can simply have negative ln x plus c is equal to 1 over 2. Of course, if I integrate this, I want to do it one by one so that you can understand what I did. So I have negative ln x plus c is equal to 1 over 2 ln 1 plus v. So here, I can simply have minus 2 ln x plus c, of course 2c is equal to c is also a constant, is equal to ln 1 plus v. So that if I bring this over to this side, if I bring this here, I would have ln 1 plus v plus 2 ln x is equal to c. So that I would have, because we know very well that ln a plus ln b is equal to ln a ab, right? So we're going to have that this is ln 1 plus v plus ln s squared is equal to c, so that we have ln 1 plus v into s squared is equal to c. I simply applied this law of logarithm here, so that I can have exponential ln 1 plus v s squared is equal to exponential c, which is also c, of course. So we have 1 plus v s squared is equal to c. But remember that y is equal to vx, which we assumed in the first instance. So we substitute our y back. So we can have that 1 plus y over x into x squared is equal to c. Finally, we can have x squared plus yx is equal to c. So we have that y is equal to c over x minus x. So this is the solution to the differential equation. To see another example, we have this problem 2. They said find the particular solution. Find the particular solution of the equation. The equation is x dy dx is x squared plus y squared all over y. Given the boundary condition, y is equal to 4 when x is equal to 1. Now, to solve this problem, the first thing we have to do is, I'm going to solve with blue. Can you use blue? To solve this problem, the first thing we have to do is to rearrange. I'm going to write solution here. First thing we have to do is to rearrange. So the equation is x dy dx is equal to x plus y squared all over y. So we have to rearrange. To rearrange, we have dy dx is equal to x plus y squared. S squared plus y squared all over xy. So this is homogeneous in x and y because, as we can see, in the right hand side, the combined, this is degree 2, this is degree 2, and this is degree 2. So the combined powers are all in degree 2. So we are good to go. The next thing is to assume that y is equal to vx. So if we do that, we have that dy is equal to v dx plus x dv. From here, we know that dy dx is equal to v plus x dv dx. So we can simply take this and substitute into this equation, so that we can have that v plus x dv dx is equal to s squared plus v squared x squared, because y is equal to vx, all over x squared v. So now we have that v plus x dv dx is equal to s squared into 1 plus v squared all over s squared v. So this can take care of this, so that we have v plus x dv dx is equal to 1 plus v squared over v. So I can simply write this as, I can take this v to this side, so that I would have x dv dx is equal to 1 plus v squared over v minus v. So this in result would give us x dv dx is equal to 1 plus v squared minus v squared all over v, which is equal to 1 over v. Therefore, x dv dx is equal to 1 over v. This implies that v dv is equal to dx over x. We integrate both sides. Integrating both sides. So we have that integral of v dv is equal to integral of 1 over x dx, which will give us v squared over 2 is equal to ln x plus c. So I'm going to bring this down here. So we have v squared over 2 is equal to ln x plus c. So we now replace our y is equal to vx. That means we are going to replace v with y over x. So we have that y squared over 2x squared is equal to ln x plus c. This is the general solution. However, we are asked for the particular solution when x is equal to 1 and y is equal to 4. X is equal to 1 and y is equal to 4. Hold on a minute, I have to check if I'm correct with that. Yeah, y is equal to 4 and x equal to 1. So this is the general solution. Now for the particular solution, all we have to do is to substitute. We have y squared over 2x squared is equal to ln x plus c. This would give us 4 squared over 2 times 1 squared is equal to ln 1 plus c. So we have 16 over 2 is equal to ln 1 plus c. From here, we have that c is equal to 8. Therefore, the particular solution is y squared all over 2x squared is equal to ln x plus 8. Or we can simply rewrite this in terms of y. Y squared is equal to 2s squared into 8 plus ln x. So this is the particular solution. Thank you very much. You can kindly subscribe for videos like this. Thank you.